Anaïs, and let's talk about atomic isotopes. As you know, they're just different by the number of neutrons inside the nucleus, and they have the same chemical properties and almost the same spectral ones. They only differ by a small shift in the Hamiltonian eigenstate's energy. This shift is subtle yet present and is known as the isotope shift. The isotope shift is very interesting to study because it gives us a lot of information about the nucleus, which is very hard and imprecise to study by itself. So this isotope shift comes from two main contributions, the mass shift and the field shift. The first one coming from the fact that two nucleus of two isotopes of the same element don't have the same mass, and the second one coming from the fact that they don't have the same volume. We chose to work on calcium plus because it is isoelectronic to alkali and it makes our calculations easier. Well, easier, but not so much, because as you may know, our system is a 20-body calculation system, so it isn't solvable by hand and we had to solve it numerically. So that is what we did. We used two different numerical methods to calculate our shifts, the Dirac-Hartree fork and the relativistic coupled cluster one. I stressed the fact that we only made some ab initio calculations, which means that we don't have any experimental bias. So what we did once we had our numerical results is that we compared them to some recent experimental data. So this is what is shown on the graph over here. So this graph shows the shift between the calcium 40 and other isotopes, so from 45 to 48. And so it compares our two methods, so relativistic coupled cluster in light blue, Dirac-Hartree fork at the bottom in medium blue, to some experimental data by Garcia-Ruiz in dark blue. So what we can see from this graph is that, first of all, the DHF method doesn't give really successful results. Well, they're quite far from the experimental one, and so from now on, we'll only focus on the RCC method to make our new calculations. But still, our RCC method, even though it gives some satisfying results, we're looking for the right direction, we're working on the right direction, it is not that close to the experimental results as we would like it to be. We still have a 10% error, which is, well, not that good. So in the future, we're looking forward to increase our precision and make some new calculations. So if you're interested in that, well, look forward to it. What we also did is that we wandered around the little new physics path that is all raging right now. And so how we did that is that we studied some king plots. So why would we study king plots, would you ask? Is to actually study their linearity. As you know, the standard models predicts only linear king plots. It comes from the standard models, it is what it is. What we did is that we gathered a lot of different spectral information from calcium and calcium plus, and we plotted a lot of different king plots for all the combinations of lines that we could find. And we were looking for some non-linearities because, well, seeing some non-linearities in some king plots would mean that the standard model would not have predicted that, and there would be something missing or something different to add into the standard model, some new physics. So that is what we did. We actually had some results. One that you can see here is a very good result, a very pretty king plot, very straight. Well, the perfect one predicted by the standard model. And we also had some not that straight ones, but I didn't bother to put them in here because they came from too few points to actually, well, for us to actually be able to conclude anything on them. So to conclude all our work from now on the isotope shift of calcium, well, we were able to isolate one numerical method to calculate our isotope shifts, the relativistic coupled cluster one, and we were able to study on some king plots. But for now, what we saw on king plots were that the standard model still is a really good one and works really well. Well, thank you for your interest in this fascinating topic. Feel free to ask any question if you have in the comments. I'll be glad to answer them if I can. And then bye.